Hi, in this video once again I'm going to tell you about a few interesting papers which appeared in the arXiv. We'll discuss three topics and we'll start with two papers devoted to results of the DART mission. As you remember, the idea of the DART mission was to test a planetary defense technology. The idea is to deflect an orbit of an asteroid with an impact. So a spacecraft is colliding with the asteroid, and so there is a transfer of momentum from the satellite to the asteroid, and thus the orbit of the asteroid is changed. This is more a technological experiment, so it's not a scientific mission actually. I underline that the task, the aim of the project is to test technology, to see if we really can significantly modify orbits of asteroids with such collisions. So the target was chosen in a very specific way. This is a small asteroid called Dimorphis, but it is not an isolated asteroid. It's a member of a binary. There is a large asteroid called Didymos, and the idea is like that. At first, Dimorphis is a small asteroid. Definitely we cannot change significantly an orbit of a large asteroid. So the size of Dimorphis is just 150 meters, and so it's a very dim object if you observe it from large distance, especially with a small camera on a spacecraft. But as it is a member of a binary system, then you can easily detect the larger asteroid called Didymos, and so you can safely navigate towards it. Then it is necessary to calculate, to measure how much the orbit of the asteroid is changed. And again, this is easier to do in a binary system. So the spacecraft was flying towards this pair of asteroids. The collision happened in September 2022. The camera on board of the satellite detected Dimorphis just an hour, slightly more, 73 minutes before the collision. And so the final operations were initiated, and finally the collision happened. The point on the surface of the asteroid at which the spacecraft hit was measured with a very high precision, about 1 centimeter. And in addition, there was also another satellite, a small Italian satellite, which observed all this process from some distance. So let's have a look at a few pictures. Here you can see part of the surface of Dimorphis and the spacecraft at the point of collision. Again, Dimorphis was observed in tiny details by the camera on board of the satellite, and so it's possible to have a very good model of the asteroid and to measure precisely the point of contact. Then we can have a look at another paper with images from that small Italian satellite. Here you see two photos. On the left you see the moment roughly 2 minutes and a half after the collision, and on the right image roughly 3 minutes after the collision. Definitely the spacecraft is moving relative to that system, and so that's why images are so different. Bright object in both images is the large asteroid Didymos. So you see that there is a significant ejecta of matter from the asteroid, and this is very important. Actually, this makes the experiment very successful, because it's not just like you collide two bodies and transfer momentum from one body, from the satellite, to another body, to the asteroid. No. Due to this ejecta, and you see that it is very asymmetric, the remaining asteroid obtains larger momentum, and this is very significant. So the conclusion is that the experiment is very successful. It was demonstrated that significant momentum can be given to the asteroid. So indeed, we have developed and tested technology to deflect orbits of potentially dangerous asteroids. However, in these papers, it is underlined that at the moment we do not know any dangerous asteroids. So there are no predicted collisions with the Earth of bodies which are really dangerous. So we are not speaking about small bodies of the size of the body which was observed in the sky above Chelyabinsk some years ago. We're speaking about larger objects which are potentially dangerous for the whole planet. No such bodies are known, but still the technology was developed and tested. And if you were afraid of falling asteroids, you can have a better sleep now. Okay, let's change the subject completely and look at another paper. That paper is about black holes in the galactic center. So everybody knows that there is a supermassive black hole in the galactic center with a mass about 4 million solar masses. However, there are hypotheses that in addition to this supermassive black hole, there might be so-called intermediate mass black holes in the galactic center. This hypothesis is based on observations of stellar orbits. They have some properties which we have to understand, to explain. And one of the ideas is that there is an intermediate mass black hole orbiting the supermassive black hole. And so with its gravity, the intermediate mass black hole modifies orbits of stars around it. It is possible to test if there is an additional body. And the idea is very simple. You need to observe with high precision orbits of stars orbiting the central black hole. And that's what the authors did, actually. Let's have a look on this picture. The authors observed the star called S2. And in the image, its orbit is shown in black. And they tested many variants of orbits of intermediate mass black holes. They are shown in this image in blue. And no deviations in the orbit of the S2 star were found. So the conclusion is that we can exclude existence of an intermediate mass black hole with some orbital parameters. What is allowed? Either an intermediate mass black hole is hidden deep inside the orbit of the S2 star, or oppositely, it has a very wide orbit. In both cases, it would not influence significantly the orbit of the S2 star, and so with these observations, the existence of such an intermediate mass black hole cannot be tested. But still, the result is very important. It significantly narrows the range of parameters, orbital parameters of such intermediate mass black holes in the galactic center, and then we have to maybe develop some other models to explain properties of orbits of stars in the galactic center. Finally, I want to show you a paper also about supermassive black holes. That's that paper. In 2021, a very bright transient was observed in the center of one of galaxies. This is really a very bright event, and that's the brightest transient if we are not speaking about quasars. Why such transients can appear? Typically, they are so-called tidal disruption events. You know that if a star passes nearby a supermassive black hole, then the star can be destroyed by tidal forces of the supermassive black hole. And there are many events of this type known. However, they are not so bright. Let's have a look at the light curve. Here it is. That's the light curve of this event. Also pay attention to the horizontal axis. This is a very long event, so several years of observations are shown here. And again, this is a very bright event. And the authors observed it and analyzed the data in details. And the conclusion is that it cannot be a usual tidal disruption event because the mass of the object involved in this accretion episode is very large. So the conclusion is quite interesting. Most probably this is not a star, but a giant molecular cloud. So the only reasonable idea to explain such a bright transient is to say that a giant molecular cloud passed nearby a supermassive black hole and then was accreted by this object, and so we could observe such a bright event in the sky. Okay, this is a very short video with some interesting results from the arXiv. Hopefully more interesting results will appear in March in the arXiv, and I'll tell you about them as soon as they appear. Bye.